So at the moment I am doing my fourth year project with Dr. Martin van Rooijk on the direct numeric simulation of turbulent entrainment. Turbulence is an area I'm really interested in, especially on a larger scale in the atmosphere. Something he told me was that the reason why he did his PhD was it enables you to think much more deeply about a subject than your undergraduate level. At undergraduate level, maybe you don't have the time or the opportunity to think really carefully about a subject which you are really passionate about and love. And I think that is why I would like to pursue a PhD in atmospheric sciences. It might be quite a broad reason, but it doesn't make it any less true or any less applicable. So my objective is to use the skills I've learned in my undergraduate degree, and I have really enjoyed learning in fluid mechanics, computational methods and environmental engineering, to learn more about the role of turbulence in the atmosphere and go really deep into that subject. So the equation I'm going to talk about now for a few minutes is the evolution of turbulent kinetic energy, which should hopefully be coming up on your screen right now. So what I find interesting about this is how hard it looks at the first sight, and it's really hard to get into. It looks a mess, to be honest, but once you start looking at the physics and once you start looking at the individual terms, then the problem starts to get a whole lot easier. So for example, you can avoid looking at quite a large portion of the equation and just look at two terms, and this is reduction and the dissipation of turbulent kinetic energy. The rest of the equation is to do with the moving around of turbulent kinetic energy in the flow. Because we know that energy is conserved through a system, we can flow of energy through the system. So you can look at the production of energy going into it, and then the transport. But then it goes in on the, and then you can see as the eddies mix with flow, you can see it going down into a much smaller scale, and then the energy is dissipated into heat on a molecular scale. By avoiding having to solve a full set of Navier-Stokes equations using direct numeric simulation, you've now ended up with 4 equations and 10 unknowns. So therefore you need to approximate some of the terms so it can be solvable. You do this by relating the fluctuating terms by the mean transport terms. You can do this using first order moment closure or second order, and the differences give you a different level of accuracy, with the second order obviously being more accurate, but it will be less robust. Second order moment closure, you end up relating the Prandtl mixing length with the dissipation rate. So this second order moment closure is most commonly used in industry, but you need to understand the limitations of it, such as right next to a boundary it's not very good, and you might need to take account of additional bodily forces such as buoyancy. So for this last section I'd just like to explain why I haven't done the mathematics subject test GRE. Because I've done an engineering degree, there are a few topics which I just haven't covered at all, and so I think it would have underrepresented myself if I have taken the test. To get onto the Dean's List at Imperial, you have to work very hard and you have to be extremely clever. So I think that my academic record has shown that I am capable of coping with any challenges I've ever come across, and I've coped with them extremely well. So I think that I have potential, and I am extremely determined, and I'll put in the effort to make sure that I make your program a success.